Hey, what's up, guys? Yeah, so previous I'm filming the video about extreme graph theory, but I would just feel like this topic is also interesting. Yeah, so I will make some video describe the function called permanence and its computational complexity, or basically some also related to the quantum computing. But in this video, I will just basically talk about definition and also give you the property why it's permanence. Give you some list some property which is common in this permanent. And I think the first time I heard about this permanent actually blew up my mind, right? Compared to like the high score determinant. So let me just explain. So the setting, right? So usually given by matrices, let's say over some field F. So which it can be real number, complex number, or finite field. And one can define a permanent of this matrices X. Let's say X belongs to unbiased matrices to be the summation of all the you consider all the I and the sigma I. So sigma I is the where I from 1 to n, and the sigma is the permutation of the symmetric group. Basically, it's the unsimple permutation. And maybe it looks hard to understand, but let's compare with another function. Basically, it's the called determinant. You do the same thing, but there is a -1 sign, which depends on the even or odd permutation. So let me just maybe using what's the standard notation? Well, it's a sign of the permutation sigma, and do exactly the same thing. Okay, so basically we know that in n by matrix is determinants, right? So for example, determinant of A, B, C, D, basically just AD minus BC. Right, so determinant of like n by matrices just takes the n factorial products, and each for each one you give the permutation whether it's even or odd. If it's odd, then you give the -1. So for the permanence, you do the same thing as the determinant but without minus sign. Okay, so a very simple way to explain the permanent basically is the permanence is the determinants without minus sign. Okay, so for example, the permanent of A, B, C, D will be just the exact representation, but without minus sign. So it's A, D plus B, C. Okay, and obviously that this is trivial, which is determinant of A, B, C minus D. Sorry, yeah, it's definitely incorrect, but it's this. Okay, so it's AD plus C minus B. Okay, so this is the permanence. Okay. But why it is interesting? Okay, so let me just show the property. So there are some common property of this permanence, right? So the first one, is permanent X is the same as permanent of X transpose. Okay, easy to prove it. And notice that this permanent also is like linear, right? So you can X plus Y is the same as so. Sorry, it's where linear in you can do the expansion. Okay, so what I'm saying is that if you like matrices, right? If you like if you basically sorry, you can do the you can compute the permanent if you know the smaller sub matrices. Okay, so but what I'm saying is that if you have x11, x12, and x21, x22, then this permanent can be written as x11 and do the permanent of these matrices. So let me just so these matrices and then plus x12 where you're just crossing this and then with using these matrices. And the x13 using these matrices. So basically D has the property of determinant, but everything with plus sign. Okay. And the third fact, which non-trivially, but you can easily prove, is the permanent usually is invariance. Sorry, permanent also is invariance under like if you permute this column vector or row vector. under column or row vector permutation. Right, so compared to the determinants, it has the minus sign, but for these permanents, it's invariant under the column or row permutation. But Gaussian elimination fails. Okay, so Gaussian elimination fails. Okay, so in the determinants, right, you can prove the following fact. It says A, B, C, D. If you add if you multiply each vector, right, times some scalar and add it to another vector, which you get a same thing. So this means that you can prove A, B, as I say, T, C plus TA, D plus TB. Okay, but you can prove that A, B, C, D is obviously the different if you take such thing. Okay, so from this thing, we know that Gaussian elimination fails, right? But in order to compute determinants, we need the Gaussian elimination. Okay. So the fact is the using the Gaussian elimination, then one can compute determinants, right, in own cube time, because you can using Gaussian elimination, and finally your matrices will be upper triangular. Okay, and the determinant of these upper triangular matrices will be the product of the diagonal. Okay, and but for permanence, which we don't know where there is a Pauli algorithm or not. Okay, so in the Valiant in computer science, Valiant in 1979 proved that the permanence of 0, 1 matrices is Sharp-Hard. And proof this require a lot of work, so maybe in the future I will give the proof. And before we finish this video, that I would introduce this Glynn's formula. Okay, so we know that, right? So if we just by definition, right, computes permanence require like n factorial term, right? And for each term, let's say you make the products, you need to compute the n consecutive number product. So it's order n. This is the products of the arithmetic operation, and that is n factorial term. Okay, but there is a way, but this Glynn formula will give you another way which reduce this to a larger amount of time. Okay, so let me just write down formula. This formula is weird, so so it's called you can prove the permanent x is actually equals to the exploitation value of, let's say, x1 up to xn. Okay, so very bad notation. Let me just change this to a. Okay, and that is x1 up to xn, where xi is basically plus or minus 1, and the technical exploitation value. So this is uniform random. I pick each coordinate x1, x2, or xn plus or minus 1 uniform randomly, and then with x1 up to xn, and then we do like a11 x1 plus a12 x2 up a1n xn, and the a21 x1, a22 x2, a2n xn, and an1 x1 plus an2 x2 up to ann xn. Right, so compute all these products and take this term per times all this, right, and then you pick x1. You pick uniform random that you compute all of these things, give you the permanence. And yeah, right, this looks weird, so hard to understand what the hell is going on. So let me just provide a simple example so that you'll get a feeling. So for example, and let's say it's ABCD, right? So in this case, that's computes the expectation value of x1, x2, and x1, x2, and a x1 plus b x2, times cx1 plus dx2. Okay. And you obviously this thing is basically ac x1 squared plus ad plus bc x1 x2 plus bd x2 squared. Okay, so if I times this, then notice that this term give you the x1 cube, x2, right? So I will compute the expectation value of x1 cube and x2. Okay, so since they are independent, right? So, but this term is actually 0 because expectation value of x2 is plus or minus 1, right? So it's 0. So obviously that this term will cancel, and the same reason for this is cancel. So remaining term will be AD plus BC, expectation value of x1 squared and x2 squared. Okay. And these two terms is independent, right? So basically it's expectation of x1 squared and expectation value of x2 squared. And since they are all plus or minus 1, right? So this is just 1. Okay, so you get AD plus BC, okay, which is the permanence of A, B, C, D. Okay, now you can, so this simple give you a reason, right? Because in this case, in order for this permanent to be non-zero, there must be the pairing of, this guy must give you some particular pairing of x1 up to xn term, and all these pairing term must exist in the permanent. So once you times this, x1 up to xn squared, there are all 1 that give you the permanent. Okay, but a very weird thing happened, right? Because you have such formula, so you can compute the permanent. Okay, so you have such formula, you have such Glynn formula, so you can compute permanent. Okay, so let me just write down. So you can compute permanent in 2 to the n squared time. Okay, the reason is that there are 2 to the n10, 2 to the n10 here, and for each operation, right? Let's say you need to do the so you just pick 2 to the n term, and for each term you need to write n minus 1 addition and the product of product of n term. So each x1 up to xn you require n squared arithmetic operation, and there are 2 to the n10. Okay, so it's, and then there are like very smart way you can like change it to 2 to the n times n10. So basically, this is probably the fast way. I think it's the fast way to compute the permanence. So from n factorial term to boils down to this 2 to the n times n. Okay, so this is a Glynn formula. And the one application of Glynn formula, which is very funny, and I think it would be like interesting to talk, is the permanence of unitary matrices. Okay, so the permanence of unitary matrices. So this thing actually showing the in the quantum computing, there's a interesting research area like in 10 years ago called boson sampling. So I will explain this maybe in the future. So, but I want to focus on this permanence of unitary matrices. Okay, so the fact is the following. So we know that right. So given the determinants, if I want to compute a determinant of unitary matrices, which is absolute value 1, okay, it's trivial because why? Because we know that u dagger times u is 1, right? So the determinant of u squared is basically 1. Okay, finish up. And the fact, which is not obvious, is basically the permanence of unitary matrices is bounded by 1. Okay, so this is non-trivial. Okay, it's not obvious, right? Because the reason is that permanent don't have such property. Right, so permanent can, so basically the permanent A, B is definitely different from permanent A, permanent B. Right, so you don't have such quantity, right? So you are not sure about whether it's maybe the unitary can be very large, a permanent unitary is very large, right? Because you only get an n factorial term addition or not. You get an n factorial term. It's not easy way to see that whether this orthogonality will make the cancel out. Okay, so the rest of the video, let me just prove the following fact. So the permanent u is bounded by 1. We can prove by Glynn's formula. It's very non-trivial. I think it's non-trivial. Okay. And okay, so okay, by the way, if you know the boson sampling, then this will be trivial. Okay. But it's also require like more basically you need a lot of work to show there's some homomorphism between the Fock space and accretion and inhibition operator. Okay, so notice that if I compute this, if I do the absolute value square of this, and I do the product of it, I say A22, A21 x1, A22 x2, A2n xn absolute value square. I do all this. AN1 x1, AN2 x2, ANN xn absolute value square. I consider this term. Okay, let's call this term B. Okay, so I want to bound B. Okay, if I can bound B, then I can bound permanent, right? So I want to bound B. I want to bound the find the upper bound of B. Okay, and then so you have products and product of number, right? So the natural inequality is the arithmetic mean versus geometric mean inequality. So AM GM inequality. So geometric mean is less or equal to arithmetic mean. Okay, so B is bounded by B is bounded by sum of this. Right, so basically bounded by A11 x1 plus A12 x2 A1 and xn square plus A21 x1 plus A22 x2 A2 and xn square plus AN1 x1 plus AN2 x2 ANN xn square. Right, so all these products, right? So they are bounded by this. Right, so let me just write down. So if you have alpha 1, alpha n, 1 over factorials, that's equal to n of alpha 1, alpha n. Okay, so we can, so this is what we're gonna do bound. Okay, and what? And we can try to bound this term by Cauchy-Schwarz, right? Okay, so Cauchy-Schwarz, so first term will be the A11 square up to A1n square, and okay, so it's no square roots. Okay, so the first term, and then x1 square up to xn square plus A21 square, A22 square, A2n square, and x1 square up to xn square power n. And let's say, so all these are n, right? So we can cancel all this out. Right, so it's they all cancel out, so we have got this. Okay. Okay, so so we got this, right? So sum of this, and sum of this. Right, so we get okay, so if you do this, then it seems like very tedious, right? You get something like very large, right? Because this is n. Okay, so if I do this with Cauchy-Schwarz, then I guess basically it will fail, right? But let me just do another way. Okay, so this method gives you a very large thing, but actually we can like we can prove this by using very good results. We can do this. So these matrices are A times x1 up to xn. Right? This is the first term of this. this is the first component of these matrices, and this is the second component of these matrices. So basically what you're doing is that suppose this is a vector, and then you just compute this, the vector norm of this, right? So basically you will compute the vector norm of these matrices. Right, so this is your numerator square divided by n and do a factorial. Okay. Right, because these are the right, so these are the component of this first vector, the vector of the first component of the vector, the second component, and up to like nth component, right? So you calculate all these absolute value square, and then you get these matrices. Right, so this is what you're gonna do. Okay, and so this is second norm, right? So it's basically bounded by the maximum eigenvalue, the maximum eigenvalue of A times the maximum eigenvalue of A and times the norm of the vector. So it's x1 squared up to xn squared divided by n. Okay, because you need to normalize it, right? And then these two cancel. So it's bounded by the lambda maximum of eigenvalue to the power n. Okay, now we finish the proof because we can say A is unitary. A is unitary, so the maximum eigenvalue is bounded by 1. Absolute value 1. Okay, so I should take the absolute value. Okay, so after this stupid work, we should prove that B is or absolute value of B is less or equal to 1. Okay. Oh, sorry, B. So B is less or equal to 1. Okay. So the permanence of A is the exponential value of x1 up to xn with if I take absolute value, then I take an absolute value of it doesn't okay, I can take as absolute value of it, right? So I can get this absolute value of it. I will less or equal to take all this absolute value and B. Or basically let's say I compute square. Maybe I don't care about square. Okay. Because B, right, it says go back to the page. Oh, why go low? Okay. So this B is this, right? So the square root of B, right? So or the magnitude or the okay, so the square root of B is the norm of this product term, right? So I can freely say that okay. And all these are 1, right? So it's bounded by square root of B. Bounded by 1. Okay, right? By definition, right? You now write down the permanent, take absolute value, and you use this Glynn formula. So this Glynn formula take all this small x1 up to xn out, and you use the this Glynn formula to show that B is less or equal to 1, but that means that square root of B is less or equal to 1. So we show that the permanence of unitary matrices or unitary matrices is less or equal to 1. Okay, that's it, and see you guys next videos.